Okay, so can everybody see the slides? Does it work well?
It's still getting them on. We don't see them yet.
Okay, okay, let's just wait a few more seconds. Does it show up now?
It looks like it's stuck on the PowerPoint screen.
It's just white?
No, it's just the first slide has not changed, and like the drop-down menu is kind of frozen.
How about, do you see the change or still stuck there?
It's
Still stuck.
Okay, I'll have to share again. How about now?
We're not seeing your screen.
Oh. So can you see the slides now? I did not use the play mode.
We have a black screen right now.
Okay. Zoom is working pretty bad today. Does it show up?
No, it's still black right now.
Oh. What's wrong? Come on. Still black?
Still bad. Oh, wait, now I see it.
Okay, how about the transition?
Yep.
Okay,
Yeah,
great.
it's working now.
Okay. I have to say that Zoom is performing really badly. Yeah. And hopefully that won't affect our second last lecture and last lecture on next Tuesday. Yeah. So, oh, by the way, so again, I want to confirm with everyone. Our final exam will be May 3rd from 10:30 to 12:30, I believe. And the exam information and has been posted on our course web page, but also is released on the official page by the university. You can check it out. And later we'll send some reminder information, I guess next week, and to ensure everybody know that and don't miss that. I will give some final. The final exam will be carried out online in Canvas. So some students came to ask me last on Tuesday, and don't concern too much about the exam content. It's pretty easy. I mean, it's not hard, but you do need to spend some time to review what we have discussed throughout this semester, because we don't have any midterm exam. That means our exam will cover all possible topics we have discussed so far. But it's open book. At least you need to review the slides. If you want to find out some answer, you can quickly reach out to that slide, right? Okay, so today we're gonna introduce a new learning framework, which is which is pretty popular. It's called the Bayesian Learning Framework, and I'm a Bayesian guy, meaning that this is my my own research area. But unfortunately, because of this class, I cannot spend much time introducing what is Bayesian learning. But I have an advanced class usually in fall, but this time will be in next spring. It's called Probabilistic Machine Learning. In that class, I will introduce in-depth knowledge about Bayesian learning perspectives. Okay, so before we talk about Bayesian learning, I just want to briefly review what we have discussed for other learning frameworks, like mystic-driven learning, right? It is mainly adopted by the perceptron, right? Learning by counting the number of mistakes. And then we have some theoretical analysis. You can bound the maximum number of mistakes you can make if your data are really linear separable, right? And another notion about learnability comes from the computational learning theory, right? That involves a key concept called PAC, right? Probably approximate correctness, right? So we define what is the PAC learnable, right? And we mean that you don't need too many examples, which is really polynomial complexity. You can, with high probability, and get your learning hypothesis to have generalization error less than some given threshold. Right? So those are mainly talking about the sample complexity, and we want to analyze the error bounds on same examples, namely, if we use our learned hypothesis to predict the future examples, what is the possible, what is the maximum error you can get, right? So we have derived that bound in a now-still learning setting, right? The generalization error bound. And under those frameworks or the ideas, we have a variety of learning algorithms, right? And we can use this framework to analyze those algorithms and look at what is the learnability for these models. And in all the cases, those algorithms try to find a function that produces a label y for a given input x. Right? This is the most learning models and algorithm we have seen so far. We can attribute them into this frameworks. Right? And today we're going to talk about another general framework. Of course, it has a strong connection to the existing framework we have discussed, which is called Bayesian learning. So there are many learning algorithms in this regime. We actually have introduced one specific one in the last lectures, which is called logistic regression. And another commonly used one is called naive Bayes. Unfortunately, due to the time limit, we don't have the chance to explain that. But I do believe that after today's class, if you look at some introductory or tutorial about naive Bayes, you get it. It's pretty intuitive. So today we're gonna first introduce what is the framework of Bayesian learning, right? So what's the difference between the Bayesian learning and the previous learning methods, right? So you'll see that actually Bayesian learning is trying to model the search of the hypothesis in the hypothesis space in a probabilistic framework. So we'll talk about how do we do that, right? And then we'll introduce two most commonly used methods to conduct Bayesian learning. And I believe everybody has heard that and heard that before, right? One is called maximum A posterior map estimation, and the other is called maximum likelihood estimation, right? We have used logistic regression as a concrete example to explain how do we apply these two learning principles, right? Now, today we're gonna put them in a more wider framework, in the general Bayesian learning framework, and see how in general these two methods work. And finally, we want to give another two concrete examples for maximum likelihood estimation, so that you are not restricted to logistic regression example, right? So by using these two examples, I think everybody will not feel uncomfortable for Bayesian learning methods, for other Bayesian learning methods. Okay, so first, what is Bayesian learning, right? So sometimes Bayesian learning is also referred to probabilistic learning. So they are exchangeable. Right? They're exchangeable. I think you can use them exchangeably. There's no difference between the two, right? So we're going to introduce two different notions about probabilistic learning. So the first notion is kind of like define the type of the output of the of your hypothesis. So it has like a loose connection to probability or Bayesian. Namely, we just want to learn a concept or a hypothesis that is a function maps the input to some probability. Right? So because it's a probability, so it must be between 0 and 1. So essentially, this is a regression problem because your label space is continuous, but this restricted continuous space is between 0 and 1, right? So we can use the prediction made by our learned hypothesis as the probability that the label 1 is assigned to this instance X, right? So if I gave some test example X, I use my learned hypothesis or concept to make a prediction. I give my output is say 0.9, and then I can interpret this 0.9 as the probability you assign label 1 to this example X. And this is the only definition of that. And you can use all kinds of previous learning principles, algorithms to learn this hypothesis or to search this hypothesis in some designated hypothesis space. So now I want to ask, what kind of model we have talked about that can belong to this notion?
It's the logistic regression.
Yes, exactly, right? It's just what you have discussed is just logistic regression, right? Logistic regression just learn this, right? Learn mapping from your input example to some probability, which is between 0 and 1. That's it, right? But the unique things about logistic regression is that how they model the hypothesis, right? So they assume the form of hypothesis is a logistic function. Right? We discussed in the last lecture, you can construct other hypotheses, like you can use Gaussian cumulative density functions to finish that mapping as well. That is okay. That's perfect fine, right? You have also other choices. So this is one notion. So it sounds like a more closely bound to our previous learned algorithms and framework, right? The only difference, the only thing that relates to probability is the output. Right? The output must be between 0 and 1, right? But there is also a second notion. The second, second notion. The second notion is more Bayesian flavor. That is, we're going to use a probabilistic criterion to select hypothesis. So the hypothesis itself can still be arbitrary functions, right? So you can define your hypothesis space, but how to search over that, how to select the best one according to the data, must be under the umbrella of probability theory. Okay, so what is that probability theory, or what is that probability criterion to select hypothesis, right? So the details is as follows, right? So again, the goal for Bayesian learning has nothing different from all the other learning framework. Given some hypothesis space big H and given some observed training data D, we want to find the best hypothesis from this hypothesis space H, right? So in our previous framework, we're going to define some loss, right? Define some loss over the training data and plus some regularizer, right? Then we're going to minimize this loss, and then and to search the best hypothesis in hypothesis space. Right? This is our previous framework, right? Right now in the Bayesian learning framework, we're going to define the best hypothesis as the most probable hypothesis in this hypothesis space. So what does it mean for most probable? Then we need to assign some probability meanings on the selection of hypothesis in hypothesis space. So we need to first assume a probability distribution over the hypothesis space H. So it's just like, okay, you have a lot of like points in your hypothesis space, right? We're gonna assign some probability distribution. Taking each point has some chance. And then given each hypothesis, we need to know what is the relationship between the data observed and the selected hypothesis, right? We need to formulate that as a probabilistic framework, probabilistic model as well. So that's the general idea. Right? So, but before we talk about the details, right? What is the benefit or the advantage of Bayesian methods? So the first one is it can provide some interpretable learning algorithms, meaning that, okay, how we assign a distribution over the hypothesis in the hypothesis space can be according to our prior knowledge, our experience. And then given this particular hypothesis, how it gets to the observed data can have another probability interpretation. So these two steps, assigning the prior and combining prior with the hypothesis to generate the observed trained data, they are both transparent. You can encode whatever your own knowledge, your own belief into that through this rigorous framework. And also, it provides a conceptual framework to evaluate other learners. That is about like using Bayesian methods to do the model selection, which we're not gonna discuss in this class. I was just to let you know, right? And finally, it also provides a tool to analyze the learning behaviors because the whole Bayesian methods are based upon the probability theorem, right? You can use all kinds of tools in probability theorems, measure theorems, random processes to analyze. It's kind of similar like computational learning theory, right? You have some definition like pack definition. You want to use all kinds of like two inequalities to do analysis, right? Similar kind of arguments can be applied in Bayesian learning framework, but now the mathematical tools will be like probability theorems. Okay, so now let us first look at how do we combine, how do we conduct. Let us look at in detail how do we conduct the Bayesian learning, right? So to talk about Bayesian learning, we need to review Bayes' theorem. Right? So I believe everybody is familiar with that, right? So the Bayes' theorem can be written in this way, right? So suppose we have two random variables, x and y. Right? If I want to compute the probability of y condition on x, we can compute it in this way. So first, we compute the prior distribution of y, and then times the conditional probability of x given y. Right? So these two use the joint distribution of x and y, right? So this part equals to p of x and y. Then we divide this joint probability by the marginal distribution of x. We end up with p of y given x. So sometimes this is also called Bayes inversion lemma because you can compute p of x given y to you can compute P of y given x from P of x given y. So to be more clear, this is just a shorthand for any possible value of the random variables x and y can take. It seems that P given the random variable x taking small, this particular value small x, the probability that this random variable big Y taking small bag Y is equal to this. Right? So hopefully no one will get confused at this point. So if we look at this Bayesian inversion lemma or Bayes theorem, what can it tell us? So, and usually in the data science or machine learning, people read the Bayes theorem in this way. So we will the probability of y or marginal probability of y as some prior probability from which we can encode our belief y before we say x. So x is usually referred to as data, some observed data. And then, and y is some model parameters we want to search over. Remember, the model parameters corresponds to the hypothesis, right, in the hypothesis space. So the prior probability encodes our belief about each particular choice of hypothesis, how likely it is, before we say any data. And the second term in this numerator, P of x given y, is often referred to as likelihood. Namely, given this particular specific random variable y, what is the likelihood we can generate or observe x? So this is called prior and likelihood, right? And finally, you divide this marginal distribution or marginal probability of x, you end up with the so-called posterior probability. So review this conditional probability y given x as posterior probability y, because we assume, okay, at the beginning, we don't see any data, right? And after I see data, my belief got changed by the data x. So I update my belief. Now the updated belief is represented by the posterior probability. What is the probability y taking whatever value given this specific data x is observed? In short, Bayes theorem is often written as posterior is proportional to prior and likelihood. Any questions so far? Is everybody comfortable with this?
Mm-hmm.
Okay, great. Yeah, it's straightforward, right? Okay, so this is just a quick refresher. I believe we haven't reviewed that at the very beginning of this semester, right? But here we just want to quickly refresh them. So in a probability theory, we have many operations like product rule, right? So so if we define A and B as the events are represented by sets, right? So the A intersection with B, meaning that both event A and B happens, right? So it's a joint probability of A and B happens. It can be written as B happens, the probability of B happens times the probability of A happens given B happens, or probability of B happens given A happens times probability of A happens, right? And some rule, this is a union, right? Union between two events, it means that either A happens or B happens, right? So it is a probability that A happens plus probability B happens subtracted by probability A and B both happen. And also we have some independence definition, right? So we say even A and B are independent if their joint probability is equal to the product of their marginal probabilities, right? Or equivalently, the conditional probability is the same as the marginal probability. And yeah, and then theorem of total probabilities, right? If you want to compute the probability of B, right? So given some mutually exclusive events, namely they are pairwise, like disjoint, and their total summation, the summation of their total probability is simply 1. Then you can compute the probability of B as this, right? So you first multiply, you first compute the probability of each AI happens, and then given AI, the B happens. You sum over all possibilities that each even AI happens. Then given each AI, what is the chance of B happens? And add them together, you get the total probability that B happens. So now let's go back to Bayesian learning. Essentially, Bayesian learning is to use Bayes' rule to conduct the hypothesis search. If we want to use one sentence to summarize it, that is, we want to use Bayes' rule to fulfill the best hypothesis search. How? Right? So because we have assigned some probability or distribution over the hypothesis space, right? So we have some distribution over the hypothesis space, and also we have some data, right? We have some model, probability model that given each hypothesis, how we're gonna generate the data, or how likely we observe data, right? So now we're gonna use the posterior distribution of hypothesis given the data to define the best.
So I have a question real quick. So the probability over H, that's like that's what you were talking about before, about how we can inform how we learn based on like our own knowledge, right? We decide what that distribution is. We assume it's like a normal distribution or something.
Yes, exactly.
Gotcha. And then the term below that one, the probability of the data given some hypothesis, you said that that's like how we expect to encounter the data given a hypothesis. I don't really quite understand that one.
That's a good question. So basically you can view like in a logistic regression case, right? So each hypothesis actually has already been represented by the weight vector, right? Because some particular weight vector, you have determined a particular logistic function, right? Will be something like that, right? 1 plus e to the power of e w transpose x, right? So suppose you have a, given this particular w, is equivalent to saying, given this particular hypothesis, how do we sample each label, right? That is the likelihood. So suppose I'm giving some observed label y and x, right? And given this hypothesis, what is the likelihood?
The likelihood of getting it correct, or?
Yeah, the likelihood is getting it correct.
I see. Okay, so the probability of D given H is the probability that we are correctly predicting the data given that hypothesis.
Yes. Yeah. You can definitely view it in that way. I mean, from a big fan of Bayesian, I would say, okay, I would rather say given is H, how H generates the data, but it's the same thing. Given H how it generates data, meaning that okay, given H how it is correctly generated data is the same thing, or predict label.
Okay, and so like generate, you mean like predict, right? It's
yes.
Okay, and so D in this case, is D the label? Is it the attributes? Is it X or Y, or is it both?
Not necessary to be to include both X, Y. Some model might involve both an X, Y, like naive Bayes, but for logistic regression, only Y.
Okay, so D is representing like our outputs, and so given that hypothesis, how likely are we to see this set of outputs?
Yes, exactly.
Okay, all right, thanks. I think that clears it up at least somewhat.
Yeah. I want to. That's why I want to first introduce the logistic regression, and then when we introduce a more general, more abstractive framework, we can match them to the concrete part. Yeah. Anyway, so and then because of this probability assignment, distributed assignment over the hypothesis space, and also some modeling of the likelihood, we can combine them together, right? We can calculate posterior distribution about hypothesis space, right? So maybe in your prior domain, before you see any data, you have some like uniform preferences over those hypotheses, right? But after looking at some data, right? And when you integrate the data information, you got some posterior distribution over your hypothesis again, right? And then maybe your preferences will be limited to a small subset. At least, for example, you might favor this particular set of hypothesis much more than the hypothesis in the remaining areas or remaining space. That's totally possible because the data can guide you and tell you which one is better fitting of the data. Okay, and then if we want to pick up the best one, right, we're gonna choose the one who has the largest posterior probability. That's the idea. Right? So because the posterior is proportional to the prior in likelihood, right? So you pick the hypothesis who has the largest posterior probability, meaning that, okay, you're gonna find the best trade-off between the prior and the likelihood, right? So you find the one who can best combine your prior knowledge and the data fitting. So what does best mean, right? So let us look at again, right? So here's the posterior probability. So the posterior probability is what is the probability that H is hypothesis, the best hypothesis, given that data D is observed. So here we can view both H and D as events. Right? D meaning that, okay, we have one event happens that we have observed this particular data set. H means that, okay, I have picked up this H as the true hypothesis or as the best hypothesis. So by using inversion lemma, we can compute, what's this posterior probability, right? And then you can take a look at which particular hypothesis whose posterior probability is the largest, means that it has the largest chance to be selected or to be the best in the hypothesis space. Okay, any question regarding the framework, the definition? Okay, so now let us look at this prior over hypothesis again, right? As we have just explained, right, the usage, and here I just want to emphasize again. So the prior probability of the hypothesis, right, reflect your background knowledge, reflect your domain knowledge, your prior beliefs about the hypothesis, right? So what do we expect hypothesis to be even before we see any data, right? That is really very common. Like like when in my office, some students came to me and say, okay, I want to do some kind of problem. Which models would you suggest, right? So, and I most of the time I can give some suggestion. Why? Because I have some prior knowledge, I have some domain knowledge, I have my own experience, right? So, and then if your hypothesis now becomes different machine learning models, I can induce my prior probability over them, right? And then given each hypothesis, what is the likelihood of the data, right? Meaning that what is probability this data point is generated by H or predicted by H. It actually reflects how much chance this data point is predicted by a particular hypothesis. Of course, if some model gives a low probability to give this a label, of course, it means that it doesn't fit data very well. And then finally, we need to divide this product P of H and P of D given H by this marginal probability to get the true posterior, right? So this is the probability the data D is observed independent of any knowledge about hypothesis. In other words, it means that if you integrate out all possible probabilities over H, what is the marginal probability, or what is final probability, right? But this term has nothing to do with H, right? So when we maximize this, right, when we maximize the posterior probability, this part is just constant. We can throw it out. Right? That's the benefit.
So you said we can throw it out, but don't we still need it in order to like look at our posterior probability? Or I guess if we're just comparing posterior probabilities with each other, then I guess we can, like, we're trying to find the best one, and so we don't need the exact values of them. We just need their values relative to each other, and so we don't need that value.
Yes, you're right.
Okay, gotcha.
So your most tasks we just want to find one hypothesis. This is one of the best. I can use that. Okay, I don't care about others. Right? But what you said is right. What if I thought I want to say, okay, what my whole belief change after saying data? My whole belief, my beliefs over a whole hypothesis space is changing, right? What is now the distribution, right? Then we do need to preserve this. We need to compute this, and in practice, this part is really hard to compute. So it's actually the how to compute this and accurately approximate this posterior distribution is the key research topic in Bayesian learning. So I'm doing this kind of things every day, right? How do you efficiently compute this? How do you approximate accurately approximate this? Right? A lot of methods, a lot of approach, a lot of methods, a lot of ideas, and you know. Okay, any other question regarding understanding this framework?
So without P of D, wouldn't our models, our hypotheses be more biased? Like if we include P of D in our analysis somehow, first of all, I think it's very hard to model. That might be the case. But let's say we include it, wouldn't it act as removing bias from our models?
No, P of D doesn't represent bias. It just represents that, okay, if you want to integrate out every possible H, like if you want to use every possible H to make prediction over D, right? And you just average them out, what is the probability? What is the final probability?
Oh,
and
okay.
As we just mentioned, right, in Bayesian learning framework, the most 99.9% of scenarios, we're looking at the one who has the largest posterior probability. Just 1 point. Like we just want to maximize this, right? We just want to find some hypothesis whose posterior probability is the largest. If you just want to find one optimal point in a hypothesis space, we actually do not to care about this because this is a proportional to the product, right? We just maximize the product this way. P of D is constant to H.
Okay.
Yeah, but of course, if you really want to compute this posterior distribution, right, you're not only concerning 1 point, right? You're looking at after seeing the data, what is the change of the posterior distributions? What is change of beliefs about hypothesis? Of course, you need to consider how to calculate this or how to approximate this. There are a lot of methods. Any other question? Okay, great. So now let us look at how do we conduct Bayesian learning, right? So we're going to introduce two framework. One is called maximum A posterior estimation, namely MAP estimation. The other is called maximum likelihood estimation, namely MLE estimation, right? So given some data, find the most probable hypothesis, right? The MAP estimation, which we denote H map, right, is just straightforward. We want to maximize the hypothesis who has the largest posterior probability, right? So again, to do that, we're gonna use the Bayes rule again, right? So by use the Bayes rule, we know that this posterior probability is P of H multiplying the likelihood P of D given H, then divided by P of D, right? As we just discussed, right? P of D is constant to H, right? So if you just, and it's bigger than 0, right? If you just if you want to just maximize this, right, we can just throw it out. It doesn't affect the maximum value and maximum, right? So, and then we can simply maximize the product of the prior and the likelihood. So this is the benefit, because posterior is always proportional to the prior multiplying with the likelihood. And if we further assume our prior of hypothesis is uniform, meaning that I don't have any preferences over particular hypothesis, or in other words, I feel every hypothesis in the hypothesis space is equal important, is equal likely to be selected as best, and then this prior is kind of uniform, right? In other words, you can view like this prior is just proportional to a constant 1, right? And then if use uniform prior, if using uniform prior for the hypothesis prior, then we do the map estimation, we actually reduce to the so-called maximum likelihood estimation. Someone has mentioned this point in our last lecture, right? So why? Because in a uniform distribution, the probability of each hypothesis is the same. It's the same, right? So we can just get rid of it, right? And then the maximization is to just maximize the likelihood P of the data given H. And of course, you're gonna look at all the hypotheses in a hypothesis space. So this is called MLE. And as we mentioned before, this usually involves, the data D usually involves many data points, right? So oftentimes we'll assume these data points are IID, independent identical distributed. That means it often written as a product, right? P of say DI given H, right? So you're essentially multiplying a bunch of probabilities. Each probabilities between 0 and 1, you multiply them together. It's very easy to underflow and truncate to be 0, right? You cannot effectively optimize them. So in practice, we'll always need to take a logarithm over this likelihood or product of likelihood and prior, and then we maximize it. Meaning that we'll do the optimization in the log domain, and to make the computationally numerical stable. Okay, any questions so far? Theorem is good, right? This is just abstraction. One layer abstraction of logistic regression, right? You can view logistic regression is just the exactly instance here. Okay. So one connection between map and MLE is that, okay, I can view MLE, maximum likelihood estimation, as a special case of map estimation where you simply choose the prior to be uniform, right? But another common understanding is just, okay, I do not care about prior. I do not assume any prior on that. I just care about the data fitting. The data fitting term here is represented by the likelihood or the probability that given this hypothesis, how to predict the data.
I have a question about this general idea. So, and I'm sure this is what you're going to be getting into, but I guess just in general. So when we talk here, when we talk about any hypotheses that we're searching, like the hypothesis space we're looking at, it's any hypothesis. Like this is general to linear, nonlinear, whatever. So it seems like then, I guess like you'd probably then want to, you'd probably need to then, I guess the key here is constraining it to the right hypothesis space to search over.
Oh, yeah, of course. I mean, if you want to conduct any learning task, you need to first define what is your hypothesis space, right?
Right, because you can't just search over infinite.
It can be infinite. I mean, even for a linear classifier like W transpose X.
Oh, well, that's true.
Yeah, it's still infinite, but you need to, I mean, even in the infinite space, you need to choose the family of the hypothesis, right, as your search over. You cannot search like into a, there's no assumption on that, then you can not do any concrete things, right?
Okay. No, that makes sense.
Okay, any other question regard to understanding this general idea? Okay, so now we actually can instantiate this MLE and map framework with logistic regression, and you can make a contrast, and you have a more concrete feeling, right? Concrete idea. But here I want to we want to give another 2 examples for the maximum likelihood estimation, so that everybody feels okay. This is pretty general, right? It is quite straightforward. So the first example is called the Bernoulli trials, and the second one is called normal distribution. And if you have taken some statistical class before, those may look very very familiar with you, right? Familiar to you. Right? So again, going back to the maximum likelihood estimation. So we want to find a hypothesis that can maximize the likelihood of the data, right? Given this hypothesis. So before we conduct MLE, we need to first define what is hypothesis space. In many cases, actually, the hypothesis space is indexed by the model parameters, right? Like if you assume your hypothesis space are linear functions, right? And each hypothesis actually is determined by a pair of weight vector and bias parameter B, right? And then you need to define a probabilistic model, which can tell, given a specific age, how to generate data or how to predict the data. For example, if it is a classification problem is -1, +1, right? You're gonna assume, given W and B, how the data point, how the label is generated, right? Is more like Bernoulli, right? Bernoulli distribution. Right? If it is a continuous variable, it can be some Gaussian distribution. So we're gonna discuss these 2 cases right now. So first example is called Bernoulli trials. Here is the example. Here is the story, right? The CEO of a startup hires you for your first consulting job, right? The CEO asks, right? My company makes light bulbs, right? I need to know what is the probability they are faulty. And said, it's sure, right? I can help you out, right? I just want to confirm that all those bulbs identical. And CEO says yes. And you say, okay, excellent. I know how to help. We need some experiment. Right? What kind of experiment it is? Right? I can ask the CEO to provide in the factory to random pick up like 100 light bulbs, right? And then we just test them. I just test them, and turns out that 80 bulbs work and 20 fail. Right? Then I just tell the CEO that, okay, the probability your light bulb fails is 0.2. This is pretty straightforward, right? A CEO will ask, right? But how do you know, right? You shouldn't say, okay, because I just found, okay, 20 failed out of 100, so the probability is 20 over 100, 0.2, right? That's not valid. You need to justify how you get 0.2. How do you justify it? Right? We need to come up some hypothesis space and probability models. Right? And then we want to use maximal likelihood estimation, and given this data, we estimate the probability of failure 0.2. Right? So my hypothesis space is the set of failures. Right? Each failure probability represents a hypothesis. Right? Of course, each probability will be between 0 and 1, right? So my failure, if I choose a particular hypothesis, namely P, right? I know that, okay, for light bulb, the chance it got failure is P, and success is 1 minus P, right? And now I have observed 100 light bulbs, right? I know that 8 of them work and 20 fail, right? And we assume, okay, each trial is just IID, right? Independent, identically distributed, right? So then I need to come out the likelihood, right? Given this particular hypothesis P, right? What is the likelihood that you observed 80 light bulbs working and 20 fail? Right? What is the likelihood? Any thought? Any thought?
Could you restate the question?
Yeah, my question is, okay, so I have select a hypothesis which is represented by this failing probability, right? How can I model the likelihood that 8 bulbs work well and 20 bulbs fail?
It will be Bernoulli's probability, NCP, p to the power n.
Yes, exactly, right? So we just need to pick up our statistical knowledge, right? So we know that, okay, in statistics, there is one distribution which can describe such kind of like data generation procedure, which is called N trials Bernoulli experiments, right? So your data D consists of is the fact that you have 80 bulbs work and 20 don't, right? So if you apply N trial Bernoulli experiment, you know that the probability of this D given your failure probability P will be, you need to compute all possible cases, right? Out of like 100 bulbs, which of 80 bulbs work, right? And then for each particular case, that particular 80 bulbs work and 20 doesn't, this chance is P to the power of 80, right? And 1 minus P power to the power of 20, right? Why? Because those bulbs are IID, right? They're working and not working are independent to each other. Right? So now we got this likelihood. And next, we're going to conduct maximum likelihood estimation. Right? We're going to maximize this likelihood to find the particular hypothesis which best describe this data or best predict this data. Right? And how can we conduct maximum likelihood? Right? We just maximize this, right? And of course, you need to take a logarithm of this and take a logarithm of this, and we can think about a more general framework. Like suppose we have A bulbs work and B doesn't work, right? And you take a logarithm of likelihood. So you take a logarithm of this combination number P to the power of A, 1 minus P to the power of B, right? And if you take a logarithm, this is a constant. You can just throw out. You maximize this A logarithm P plus B logarithm 1 minus P, right? And now you just take a derivative, right? You just take a derivative with respect to P to be 0. You can obtain the optimal B, optimum P, which maximizes the likelihood is B over A plus B. Right? So now you substitute 80 for A. You substitute 80 for A and then 20 for B. You get the chance, right? The probability is 0.2, and you can report it to your CEO. Any questions so far?
So that equation at the bottom right, that's like the one that naturally comes to mind when we see a problem like that. But you said you can arrive at that by taking the derivative of the equation that you wrote above, and then like setting that to 0 and solving for that.
Yes. That's the whole procedure, right? So I want to use this example, right? I guess most people will feel it's too simple, right? But this is a very good illustrative example, like how do we conduct a Bayesian learning using MLE principle. First, we construct hypothesis space, right? Each hypothesis is actually a failure probability. So now if I want to use MLE estimation principle to estimate or to find this hypothesis, namely the failure probability in hypothesis space, right? What should I do, right? I need to first model, given this particular failure probability, namely a hypothesis, how we predict the success and failures of the observed bobs. Right? And here we use the so-called N-trial Bernoulli experiments, right? And then we maximize this likelihood, and then we find that the optimal hypothesis, namely the optimal failure probability, is just the observed failure, number of observed failure, over number of observed success plus number of observed failures. Does it make sense? Yeah, someone asked, okay, what if I don't use MLE estimation, I use map estimation? Then the P of best is not necessarily B or A plus B. Why? Because I need to count for P of H. Right? If I have some non-uniform distribution over the failure probability, then you take the derivative of the probability and set it to be 0, then this probability might not be just the proportion of the observed failure. Any question?
Yeah, so really quick. So if P of H was not equal to 1, what does that mean like physically in this example, that like not all light bulbs have an equal chance of like, I guess, like what's the hypothesis then in this example?
Oh, the hypothesis is the failure probability. It's a probability. Like you can view,
right? Okay.
The hypothesis is just some failure probability is 0.5 or 0.1, right?
So right. So in other words, if you knew that there's some distribution of how likely a given light bulb would work, because we're assuming under this MLE framework that probability is going to be equal for every light bulb.
It's not equal for every light bulb. It's equal for every possible failure probability.
Okay.
So the failure chance to be 0.1 or to be 0.5, they are the same.
Right, because right. Okay, I see. But then we're saying then if there was, for whatever reason, if you knew that there was a distribution to that rather than being the same, then we could incorporate that.
Yes, yes.
Okay.
Like if I believe the failure probability has larger chance to be 0.6.
Sure.
And then be 0.1, then your final best probability won't be like B or A plus B.
Right, I see. Okay, thank you.
Okay, great. So this model assume is called Bernoulli, right? Of course, you could assume a different model, right? And we'll consider other models and how to learn their parameters. This refers to a second example. It's called normal distribution, right? So in our first example, Bernoulli trials is talking about, okay, what you observe is kind of like binary, discrete, right? Failures or successes, right? So what if your observation is a continuous value, right? This usually referred to as regression problems, right? Again, we mainly use MLE as an illustration, but it is easy to convert it to the or extend it to the map estimation, right? So, so this time, right, we assume our hypothesis space consists of real value functions, right? So input x, okay, in general can be assumed is a d-dimensional input vector, right? But output is a real number, y. And again, given each hypothesis, we need to model how we use that hypothesis to get the output, the continuous output. Right? You can say it's predict or to generate, whatever, right? But you have to give some probability meanings, right? So how can we do that, right? Well, here is often used assumption. So we assume the input is drawn randomly, right? And then there is some ground truth function f to get f of xi, which is the ground truth output. However, because of the imperfectness of the real world, we often assume the observed value is perturbed by some noise ei. So namely, if this is your observation, right? So always assume it is some prediction made by a ground truth function and then corrupted by some noise. And how do we model this noise? Right? So the most commonly used assumption, okay, is assuming this noise comes from Gaussian with zero mean. So this is also referred to as a Gaussian white noise. Right? And Gaussian white noise is very widely used in electrical engineering or electrical things, electrical applications, engineering applications.
So are we actually generating this data, or are we supposing that the data is generated in this way? And like, what is f here? Like, are we defining an f, or are we just saying there
is the ground truth mapping which gives the output?
So we're trying to discover that, right? That's, you know.
Yeah, we're trying to discover to approximate that.
So yeah, we're not generating any of this data actually to solve this problem, right?
Yeah. But if you want to approximate f, you have to assume the procedure that how your final observation is generated, right?
Mm-hmm.
Like only when I assume, okay, given some input in what kind of procedural steps I end up with this output, I can inversely infer this f.
Right.
My modeling assumption is also encoded in this generation procedure.
Gotcha. Yeah. Okay.
Okay. So here we'll use this. Most commonly used assumption or generation assumption is assume, okay, your ground truth value is corrupted by some white Gaussian noise, Gaussian white noise. So namely, we assume that, okay, your observation is f of xi plus some Gaussian noise ei, right? So now, given this model, right, suppose we have collected m training examples xi, yi generated by this process. And now we can model, given some hypothesis, h, right, how the label was generated, right? If h is the ground truth, h is the one we think is best, right? How should we assume h generates the ground truth yi, right? So because of the previous model assumption, we know that the difference between the observed output and the prediction made by a hypothesis should follow a Gaussian distribution because this is a Gaussian noise. Right? And then we can immediately obtain our likelihood. That is, given the hypothesis, given your input xi, your yi comes from a Gaussian whose mean is your prediction, but whose noise is some whose variance is some noise variance, which is sigma squared. Right? Let us just assume sigma squared is there. That's where we get this likelihood. So the probability or the likelihood of observing one data point, xi, yi, if it were generated using function h, right, using some hypothesis h, right, it is a Gaussian likelihood. And now suppose we have a saying m independently distributed, independent and identical distributed examples. So the likelihood or the probability of the data given this particular hypothesis is the product of those Gaussians. And then we want to, given this likelihood model, right? Given this likelihood, we want to inversely to find out the most likely hypothesis, right? By using maximal likelihood estimation. How can we do that? We just maximize this likelihood, right? And we try to search over the hypothesis space and which hypothesis can give the largest probability, right? This actually reflects that using this hypothesis to generate data as the largest chance, or in other words, using this hypothesis to predict the output value, it is most accurate. Any questions so far? Okay, great. So, so the remaining things is kind of like I believe many of you may have when you took your statistical class, you have saying this, right? But let's just go through this again, right? So you're maximizing this joint probability. You're essentially maximizing this product of the Gaussian likelihood, right? So how do we maximize that? Of course, we cannot. If we just multiply them together, it is easy to get numerical issues, right? How can we do that? Again, we take logarithm to simplify, right? And if we take a logarithm in that, the product immediately becomes the summation, right? So it is sum over 1 over sigma, those constant subtracted by this square error over 2 sigma squared, right? Of course, this constant does not affect the maximization procedure. We can throw them out. So finally, we're essentially maximizing a summation of the square errors over the training data, right? And of course, you have to put minus sign here. Right? So if you get rid of minus sign, maximum likelihood estimation is equivalent to minimizing the summation of square error, right? Because it's 2 sigma square is constant, right? We actually do not know its value because it's just a positive constant. We can throw them out. It doesn't affect the maximization, right? So now we can see that when we perform the MLE estimation of your hypothesis, right? So you're essentially minimizing the square loss on the trained data. And if we can further assume each hypothesis is parameterized by a linear function, so MLE, maximum likelihood estimation, is essentially to what? Least mean square regression, right?
Isn't this essentially the same problem we're solving in the neural net?
Can you be more specific?
So our loss function, when we have our loss function for our neural net, at least from what we've picked, from what we talked about in the lecture, is just the same setup as the SSE. It's the difference between our true and predicted label given from and the predicted labels from the neural net. And we're just minimizing the loss of that over all of our training examples. Like this looks like a similar formulation. Yeah.
So for a neural net example, right, we just replace this linear function by the neural network output, right?
Right, exactly.
Yeah, but when we define those learning framework, right, when we define least mean square regression, when we define the learning for the neural networks, we just come out loss, right? We're saying, okay, we define loss because we want to minimize the difference between your model's prediction and the ground truth, right, will just come out as loss. But interestingly, right, we found that if we formulate our learning in a Bayesian framework, right, and assume, okay, your output is corrupted by some Gaussian noises, and then you maximize the likelihood, and finally, the two frameworks or two principles end up with the same objective function to optimize.
Right, it's pretty interesting.
Yeah, this is also called a probabilistic explanation for least square regression. Right. So now we can try to compare the two perspectives for linear regression. Right. Of course, similar kind of observation arguments can apply to neural networks. Right. So for the same objective function, right, from loss minimization principle or perspective, right, our goal, the motivation to propose such an objective is that, okay, we want to minimize the difference between the square loss error of our prediction, right, so that we just minimize the total square loss, right. But from Bayesian perspective, right, this objective reflects the assumption that the errors are normally distributed with zero mean and some fixed variance. So this similarly two very different motivation and ideas in learning end up with the same objective function. So this is a very classical but very amazing connection. But actually, in non-Bayesian learning framework and Bayesian learning framework, in many models, they will end up with like strongly connected or even identical final objective function. This is just one case. Any questions so far? Okay. So yeah, through those two things, simple examples, we have finished the introduction of the Bayesian learning framework. And because of the time limit, we cannot introduce more models. But we do believe that those high-level idea, those key principles have been delivered to everybody. So in the future, if you're interested in doing this kind of things, hopefully this will be a good start, right? And so to summarize, what is Bayesian learning? Right? It actually characterizes another way or give another criterion about the best hypothesis on data set, right? In our previous framework, non-Bayesian framework, we just, what we do is just come out some loss, right? Come out loss function and measure what is the penalty, what is the cost of your current model prediction, and by contrasting to the ground truth, right? You can come out some kind of a loss function, and you just minimize the loss function to enforce your model to be closer and closer in predicting the ground truth, in predicting the examples and to the ground truth labels, right? But in Bayesian learning, it put everything in a probability framework. You assign a prior distribution over the probability space, and then given each particular hypothesis, you model how likely this hypothesis generates the observed data, right? And then when we do the learning, we do the if we do map estimation, we're actually combining the prior and the data information in terms of data likelihood. So this is actually a pretty elegant and powerful framework, but it still renders a strong connection to our loss-based learning principle, right? And then we introduced the two commonly used learning methods. One is called maximum a posterior. The other is called maximum likelihood estimation. Right? Maximum likelihood estimation can be viewed as a special instance of map estimation, right? And also we saw two examples of maximum likelihood estimation. One is called Bernoulli distribution, which is very often used for classification problems. And the other is a normal distribution. Again, it's very often used in the regression problems. So for simple problems, we expect that you should be able to apply both MAP and MLE to conduct a Bayesian learning. So any questions so far? Okay, great. So let's stop today. So in the next lecture will be our final lecture. So we'll give some practical suggestions about machine learning and how do you embed machine learning in large systems, and then we'll give a review about a review guidance, right? If you want to, to help you to prepare for the final exam. It'll be short, but it will be informal. It'll give you some strategic suggestion to prepare for the final exam. Okay, thanks.